So, are you seeing my first slide now? Okay.
Yes, yes.
Yeah.
Yes,
Very
Professor.
good. Thank you very much. And thanks for the invitation to present at this talk. I'm sorry I wasn't able to come to Balıkesir, but this is the next best we can do is by video. I changed my title slightly because I want to emphasize how fractional models sort of appear naturally in complex media or in different areas of physics, but especially with wave propagation in my case. If I had come to, let me see, I would have liked to come as the Vikings did to the Mediterranean and to Istanbul, maybe even to Balıkesir, but that was not possible. Now, this was how they traveled 1,000 years ago to what was at that time Constantinople. Now, I came into fractional calculus through a lucky meeting between physics and mathematics, because Wen Chen, who many of you know, who later was a professor at Huai University in Nanjing in China, had a research stay in Oslo from 2002 to 2004. And we collaborated from then until his untimely death in 2018. Now, I came with the problem of trying to model attenuation in ultrasound, which followed strange power laws, which weren't sort of possible to express with normal wave equations. And Wen Chen came, of course, with a very good mathematical background. And when these two came together, this resulted in some papers where we described this with fractional calculus. And so there was a special issue dedicated to the memory of Professor Wen Chen in fractional calculus and applied analysis in 2019. I had a paper there as well. And that was an analysis of one of the equations we came up with, a wave equation with a fractional Laplacian, which was what Wen contributed at that time. So that was how I got into this. And since then, I see fractional calculus as a sort of a way of describing a tiny subset of the very complex and understanding the physics of wave propagation in complex media like biological tissue, which is where I come from, rock physics and sediments. And I'm going to focus on sediments in this case, so not the vessel tree of a kidney and how waves propagate there, but rather how do waves propagate in wet sand and in under the ocean bottom. And so why do these media often exhibit power law frequency characteristics in terms of attenuation and dispersion? And can we uncover the physical basis for non-integer or fractional derivative descriptions of waves in these media? Now, maybe it's inappropriate of me to say this in a mathematical conference, but there is a danger, especially in physics, to be lost in math and to just play with maths and lose the sort of touch and the connection to the real world. And Sabine Hossenfeldt, a German physicist, wrote a book about this, and she was especially concerned with string theory and multiverse theory, where there is a lot of math and who knows how much physics. But I think fractional calculus is in the same situation. There can be too much math and too little physics. So that's been my work, sort of to try to connect it to the physics. And in doing that, I've worked with books like this, Theory of Linear Viscoelastic Behavior in various forms by Churgel and by Bland, and applied books like Diagnostic Ultrasound Imaging, but Physical Acoustics, Acoustics of the Seabed as a poroelastic medium, and Marine Acoustics. And of course, coupled this with, for instance, Mainardi's book on fractional calculus and waves in linear viscoelasticity. So, and that's what resulted in my own book, which the history of my own book, and thank you, Dimitri, for showing that book. But I wrote in that book that I thanked anonymous reviewers of several papers who have given the ideas of this book some resistance, because I tried to publish in the acoustics literature about fractional models, and that wasn't very easy. But I did publish some with colleagues, but they always met with resistance, and so this convinced me in early 2016 that this topic warrants an entire book and not just short research papers. So what am I talking about when I want to talk about wave propagation? I'm in the underwater acoustics scenario, and this is such a scenario where you have the sea surface on top of the image here. You have the bottom as the sort of the horizontal line, and you have the bottom sediment, the sand, for instance, here. And we have a source, kind of a sonar source, which transmits into the water. But some of these waves will propagate even into the sediment, and they will travel in the sediment in a way which is different from the water. It will also convert from pressure waves or compressional waves to shear waves, and they might come back again. So if you want to really study long-range propagation in water, you need to understand the sediments as well. And of course, it's interesting in its own right in sort of mapping and investigation of the sediment by itself, but so there are several approaches to this. There are two sediment acoustic theories which are very different, and I'll come back to that. So the outline is really, I want to go into first maybe a reminder for some of you, or maybe it's new for others, but the frequency domain analogs of fractional derivatives. Then I'll go into this grain sharing model of sediment acoustics, which, although not formulated as a fractional model, is a fractional model. I'll look at the prevalence of half-order models in physics and how that applies to the Biot poroelastic model with turbulence. Starting with the frequency domain. So think of I'm repeating stuff now, but think of a sequence of a function, its derivative, second order derivative, first order integral, second order integral, and we do the Fourier transform of the derivative is the same as multiplying by I omega to the power of the integral. And just a reminder, the Fourier integral is an integral where you multiply by a complex exponential kernel, very similar to the Laplace transform. And that results in a sequence of the Fourier transform, I omega times the Fourier transform, I omega to the power 2, to the power 1 to the minus 2, and so on. And from here we get the one way of defining an arbitrary order fractional derivative, which we can write like this in the time domain. But in the Fourier domain, it's just multiplying the Fourier transform of the function by I omega to the power alpha. Let me turn on the pointer here. So, like here. I'm doing this as a kind of engineering kind of approach to mathematics. I don't care about initial conditions and exact definitions here, but I hope you get the idea anyway. Now, this, if we look at this Fourier transform, we can have a sort of a Fourier approach to how to define a fractional operator, because I omega to the power alpha can be divided into an integer part, I omega to the power m, where m is the smallest integer larger than our desired order, and the remainder, I omega to the power alpha minus m, where this becomes a negative order here, a negative power. So we have a multiplication of two parts in the Fourier domain. I noted this by the multiplication sign here, a first part and a second part. And when you have a multiplication of two parts in the Fourier domain, that means you have a convolution in the time domain. And so what are we convolving? We are convolving, of course, the ordinary derivative from this integer order term here. And we want to find the inverse Fourier transform of this I omega to some non-integer power, negative power. And we can find the Fourier transform of that because it's a standard Fourier transform. A power law in time transforms into a power law in frequency. And don't look too much in the details here because it's a little bit involved, but it's not really difficult, but it needs to look carefully at indices and so on. And there is a gamma function, which there always is in fractional calculus. I rephrase it so I get it in the I omega to the alpha minus m, and then I get the temporal power law like this. So what does this mean in terms of the Fourier approach to fractional operator? It means, I'm repeating now, my product of two terms. So it's a convolution between a normal derivative of order m and a temporal memory function. And so that's the fractional Fourier transform is a convolution of those two. And now the odd thing about a convolution and a derivative is that, like here we have a derivative of a function convolved with another function. We can move the derivative around. So we can move it to from the f to the g, or even to the product, or to the convolution. And so this gives us the sort of at least two flavors of the fractional derivatives, which you are very familiar with. We can do the convolution, then the integer order derivation, and we end up with the convolution first, and then the integer order derivation. Or we can do the integer order derivative and then the convolution, so then the derivative is inside. And this, of course, is the Riemann-Liouville and the Caputo definitions. But this coupling with the frequency domain, that's very important for the coupling with physics, and this is sort of although it leads to two different fractional derivatives, and there are numerical considerations whether you should choose one or the other. That's beyond what I'm talking about here. But the link to the power law is very important, because we have lots of power laws in physics. And let me look first at the grain sharing model of sediment acoustics, which I'm sure is not familiar to any of you. But this is, you have 2 grains of sand in this big pile of sand here, 2 tiny grains of sand, and then there is a pore fluid, if you like, or water. And then there are some small micro structures, micro asperities is what they're called. And then they, as an acoustical wave travels through this, it moves these small grains of sand maybe a little bit differently. So there is a sort of a friction between the two through this pore fluid film and the micro asperities. So there's viscous dissipation there. This is a model which was derived by a colleague of mine, Michael Buckingham, at San Diego at Scripps Oceanographical Institution in California around the year 2000. And he came up, I'm copying directly from his paper now, he came up with these 2 equations, one for the pressure wave, one for the shear wave, and they look pretty complicated here. But the important thing is to see that first we have a Laplacian and a second order derivative in time. These are the terms of the lossless wave equation. And then there is some 2 terms which are really quite similar. There's a temporal derivative, there is a Laplacian, and then there is a convolution with a kernel. So this is the compressional wave. The shear wave is slightly more simple, a normal derivative and a Laplacian and a convolution kernel. And this convolution kernel was defined both in the time and the frequency domains, but in the time frequency domains, it was given as a power law. And now you start seeing the picture here, I hope. There was one h sub p for pressure wave, one h sub s for the shear wave, but in most cases we just make them similar, and so these 2 terms will merge into one. And this kernel now is equivalent to a fractional derivative of order alpha minus 1, and that's the important thing here. So when I'm repeating now Mike Buckingham's wave equations, but rewriting them in terms of this terminology with fractional derivatives and making the kernels similar, it became a lossless wave equation plus a loss term with a fractional derivative in time. And the second one became a loss term, if you like, or a second term where there is a fractional temporal derivative. And this is what Vikas Pandey and I did in 2016, where we explored this similarity. And there's no approximation or anything here. This is exactly the theory which he described in 2000, but which we rewrote in fractional calculus. So this is a very nice example of, if you search some of the physics literature or acoustics literature, you actually find fractional equations there without the people who derive them knowing that they are fractional equations. And of course, what we have here is what is called a fractional Kelvin-Voigt wave equation for the pressure wave and a fractional diffusion wave equation for the shear wave. And we can draw up some equivalent medium models in terms of a spring and a fractional damper for the pressure wave and a fractional damper by itself for the shear wave. So fractional derivatives are present but hidden in the original formulation. I think that's quite interesting because it's not the only example. Now, where did Michael Buckingham get these power law operators from? Well, he got them from a book by John Gittus in 1975, Creep Viscoelasticity and Creep Fracture in Solids, and a chapter which is called Modeling Behavior of the Notting-Scott-Blair Equation with a Maxwell Model, where he talked about a nonlinear dashpot in the Maxwell model, which hardens up with the passage of time. It's only time which changes it, not the stress, and he called it strain hardening. And so the underlying model here is something like this: a Maxwell model with a spring and a damper, but the damper is dependent on time and gets a larger value with time. So he called it strain hardening. In fluids, it's called non-Newtonian, and it's called the Riopecti, this property. And Michael Buckingham went on to derive an even more accurate model, where he had a series of dampers instead of a parallel combination. But I'm not going into that. But this model has been further developed, and we are working on making a fractional derivative description of that one as well. It's not as straightforward as the first one. Now, we've taken this model and we analyzed it, and saw also that this model actually leads to the Lomnitz creep law. If you look at the creep response, the relaxation response is a fractional derivative, the creep response is the Lomnitz creep law. And we also translated into the electrical domain, and we can model the constant phase element. This is what we published earlier this year in terms of a time-varying inductor in series with a resistor. So that's one example of how these fractional models come out sort of automatically. Now, I want to talk a little bit about the prevalence of half-order models. And of course, Professor Machado talked about Leibniz and the discussion of the half-order derivative with the L'Hopital from 1695. Also, in one of the early fractional calculus books, Oldham and Spener from 74, there is a chapter called Semi-derivatives and Semi-integrals. So they were aware of this sort of special role, although this was mainly a mathematical approach, not so much physics. And of course, the first physical problem, the Abel's mechanical problem, where he generalized this tautochrone curve, the curve where no matter where you drop a ball, it ends up at the bottom at the same time, which has a square root in the integral transform here, or integral operator, is a sort of Caputo derivative of half order. So here we also have a half order model, and the inverse is a half order integral. This was in 23 or something like that. He came up with this when he was something like 20 or 21 years old. Another half-order model which comes out naturally is a cable model, where you model a cable, like a cable here, with the lumped elements, inductors, resistors, parallel resistors, capacitor, and we often simplify it to neglect the inductor and neglect the loss resistance here. And we can find the input impedance as something like this, which for low frequency is inverse proportional to square root of frequency. And the impedance goes like this. It falls with the frequency to the -half and then levels off. This is the typical loudspeaker cable, and it has a fractional characteristic up to about 1 kilohertz. So you can actually measure this if you just take a typical loudspeaker cable and measure it. So, oops, what happened now? Yeah. So this ends up being a fractional model of -1/2, fractional integral of order 1/2. You have a mechanical analog to this with springs and dampers, which also with an approximation ends up with the square root of I omega. So we have a half-order model at low frequencies. And this, when we make all the springs the same and all the dampers the same. And this is also the same as the Rouse polymer model. So it's the simplest model for a polymer, where you have beads in a viscous medium. And so it's comes both from mechanics and from polymer, the field of polymers. Another half-order model is in what's called viscous boundary layer problems, where you have a gas or a fluid flowing past a fixed boundary. Then the velocity will be 0 as a boundary condition. It will increase, and the size of this layer is inverse proportional to the square root of frequency. And if you want to find a wave equation for how an acoustic wave travels in this viscous boundary, then this is an equation which you can find in the Fundamentals of Physical Acoustics by Blackstock, which again has these terms, which is the lossless wave equation, then the loss term with 1 over the square root of tau. And it doesn't take too much to see that this is a fractional derivative of order -1/2 or a half-order fractional integral. And even here, it was just expressed in Blackstock's book as an integral equation like this, no mention of fractional derivatives, but it is exactly a half-order fractional integral, just comes out that automatically. The last example I want to show is in this second sediment model, the poroelastic model, and I'm showing here a model of a skeleton or a bone. So the dark part here is the skeleton, and then there is a fluid inside the skeleton. So it's a poroelastic medium. There's a fluid in the pores, if you like. These are not continuous pores, but pore spaces, I guess. And if you want to look at flow in such pores, and we have to idealize it to a circular pore. So with laminar flow, we get the parabolic flow profile. With turbulence, we get the more chaotic one. And this is circular. Whenever you get have a circular geometries, you get Bessel functions. And so the drag coefficient in a circular pore, this in the frequency domain, is given by this Bessel functions of the first kind, or modified Bessel functions like this, where there is a square root of frequency in the arguments, which is very complex to work with, but a fairly good approximation is the square root of 1 plus I omega scaled. And I plotted the real part and the imaginary part. They match fairly well. They matched at 0 frequency, and they match with the parallel asymptotes. If you look at the dynamic permeability of 1 over this, it's 1 over the square root of something, which is actually a Kohler-Davidson model, for those of you who are into medium models in dielectrics. And so we are going to use this because this is going to change an interesting wave equation into a fractional one. So my last point is look at this BO model with turbulence now. And as I said, there were two families of sediment models. I talked about the grain sharing model and its further developments. The fundamental model here was fractional. Now I'm mentioning the BO or the BO-Stoll pore-elastic model, and I'm going to go into the turbulence. It's been developed also. It's a very complex model, actually. Even the fundamental model is very complex. So we describe it by 11 physical parameters: porosity, permeability, tortuosity. It's used for sediments, it's used for bone acoustics, it's used for brains. And characteristic for it is that there will be two compressional waves, a fast one, which is like the one we expect, and the slow one, where the movement of the skeleton and the fluid are out of phase. In the normal mode, they are in phase. And there is also a shear wave, which is supported here. And I'm going to look at only the shear wave because it is the simplest to formulate. And even that is not very simple. And I'm not going to ask you to look at the details here, but this is from one book, Jens Holm, who actually was my PhD supervisor in Trondheim in the 70s and 80s. And there's a determinant here producing an equation like this. And we get a ratio of the wave number and the frequency squared as a ratio like this. And there is a factor F here, which is this drag factor or viscodynamic factor. It's usually 1 when there is laminar flow, and then it increases with frequency with turbulence. And surprisingly, this model here is actually the standard linear solid model, the Xeno model. It comes out of this very complex model, but it is the same. It has the same structure. So a spring in parallel with a spring plus a damper. When the turbulence factor is just 1, low frequencies. Now what, and I showed this a few years ago. I'm surprised that nobody had seen that before, but there were, I guess people are too hung up in all the complexities there to see the simplicity sometimes. But if now I take this equation and I change from the 1 for the viscodynamic operator to this square root, and I approximate it even more to just neglect the constant part here, then this has to do with a half-order derivative. And when I do this, and the operator is approximately half-order derivative, then for high frequencies, we get a wave equation, which is no longer a Zener wave equation, but a half-order fractional Zener with, again, with the lossless part, then half-order derivative in time and a Laplacian, and a 2.5-order derivative in time, 2 loss terms. And so this applies now only to high frequencies, and I can plot the attenuation and the wave speed. And my new wave equation is the red one here with the turbulence term, and it matches the black, the sort of exact one at high frequencies in both cases. And so even here we get a fractional derivative wave equation coming out of present term. I'm not playing with the terms, not making things which are non-fractional into fractional. I'm just analyzing standard terms in the theory, and they turn out to be fractional, at least in the asymptote. The challenge for us now, which we're working on, is to find a fractional partial differential equation which fits the entire frequency range. It matches the entire black curve here for both low and high frequencies. So that sums up my talk. Let me see. I talked about frequency domain and definition of fractional derivatives, and how via convolution we can easily come up with the 2 ways of defining a temporal fractional derivative, either the Caputo way or the Riemann-Liouville way. I talked about how the grain sharing model of sediment acoustics naturally leads to not just 1 but 2 fractional partial differential equations, one for the Kelvin Voigt equivalent for the pressure wave, and a what is it called, the diffusion wave, fractional diffusion wave equation for the shear wave. I looked at how half-order models naturally come out in several physical problems, and how when we apply that to the turbulence part of the bioporalistic model, even there we can get the fractional partial differential equations, but so far only for as a high frequency asymptote. So that concludes my talk, and I thank you for your attention, and I hope to be able to meet you in Balıkesir or some other place at some time in the future. So thank you very much.
Thank you, Professor Holm, for your nice presentation. Now it's time for questions. Before I give the microphone to my colleagues, I would like to ask you to put one of the first of your slides when you show that book about mathematics, Lost in Mathematics.
Yeah. Maybe it's an insult to show that in a mathematics conference, but I hope you take it positively.
No. That is why, yeah, I want to, yes. So she was talking about string theory and membrane theory and so on. Supersymmetry also, which was a very popular field in 80s. Everybody, especially young American fellows from top-level universities, developed string theory and with, two-dimensional motion, etc., many dimensions and compactification and so on. So this theory was destroyed by book of Nobel Prize Tuft from Netherlands, who proved that there is no connection with reality. Supersymmetry, which is also nice mathematical constructions. For example, Dumitru and anti-Dumitru, Sverre and anti-Sverre. So everybody has it's a very nice concept, but it was destroyed by CERN experiments about the standard model. So mathematically, this string theory is fine. Even now, people may work. Supersymmetry, you cannot. But unfortunately, when you try to go to reality, then there is a big problem. You put fractional calculus. Also seems to be in the same category if you take a model and replace and produce some figures and produce some stability, existence, uniqueness. Although mathematics is correct, you can introduce things like initial conditions, which totally are unphysical, and you can find, for example, in optimal control, equations containing unphysical meaning, so you cannot implement them. That is clear. So what I like in your talk that you try to connect the mathematics with physics, I mean, construct models with physical meaning. The same idea is for biology. The same idea is for economics. So before 2004 and in the neighborhood of 2004, people believed that fractional calculus is coming due to frictional model. But let's look to Hubble's problem. Where is the friction? Is there any friction? No. It's natural, the integral. So what is my opinion, of course, to be very careful when you play with 1/2. There is square root in mathematics, which gives many good results. There is no gamma function because gamma function is exact. So this type of models like Abel, which was generalized then by Sonin and even Abel himself, and it is very good to any order, introduce Caputo derivative, but from one point of view. In Caputo's paper from 1967, the Caputo derivative is introduced from physical viewpoint. So also in 1832, it was introduced by Liouville. And if you also presented your very nice, the very nice book of Holm and Spanien, where it was a connection between Riemann and Caputo. So this Caputo derivative for fractional calculus appears in at least 4 times derivations, 4 different types of derivations.
Before it came sort of in, found its physics or was
Yes.
connected to really to physics. Yeah, and I think
Yes.
that's true. That's true.
Yes. So fractional calculus is not in the same category like string theory. String theory was proved that doesn't exist by experiment. But as you explained here, you find very nice models for 1/2. And this means that for 1/2, the fractional model are validated. Now, the question for young people, not to mix the minds, for young researcher, of course, fractional calculus are validated, but not for all alpha. For all alpha, they can produce math models, which are correct, absolutely correct. But for certain alpha, we can have physical meaning, not for all alpha. If you are able to find a model, fractional model for alpha between 0 and 1, or for alpha between bigger than 1, that we are in exceptional category. Exceptional category. So these are very important topics. So I kindly ask Nejati to open this topic during our roundtable. Fractional models or fractional calculus with physical meaning, not geometrical, because we don't have biological meaning, economical meaning. There is a book of Caputo. This is the book. When he tries to give economical meaning to the fractional models. So there is also a biological one. Carla and Amin Jajarmi and myself, we are trying to speak about to give a validation. So the problem is, what is alpha with physical meaning? Alpha can be irrational. You cannot measure.
I've seen people sort of, I haven't gone into myself, but that there is more easier to argue for rational orders than irrational orders. I found that interesting to think about, but I haven't really gotten anywhere with it. But it's true that. But I think that Hosenfelder's point is that we can be so obsessed with beauty and beautiful equations that we lose the sort of it has to be rooted in some physical experience, physical experiment or physical measurement. And so that's her point, beauty. And for sure, fractional equations are beautiful. So that's why I think that there is a danger of sort of emphasizing the beauty so much that we forget they are actually supposed to correspond to reality also.
I fully agree with you. Jordan, do you have any question or any other question? Please feel free to ask. We have enough time. Professor Nejati, where are you?
I am here, dear professor. I am here.
Please ask a question, because the talk was very good as the previous talk of Professor Machado.
Yeah. Is there any question from the participant? Might be it is better to ask rather than
sure.
I would like to ask a question, if you allow me.
Yes, please.
My name is Cihan Bayındır, and I have a question for Professor Holm. So in your paper, which you showed that, well, the Buckingham's paper can be re-expressed using the fractional derivative. So, well, it was related to the stress propagation in the grain sediment model, but I would like to ask a question. Well, did you have any extensions of this work to the underwater acoustics case? And especially what I'm asking for, like, as you know very well, there are two main models for the underwater acoustics. The pressure equation is either expanded in terms of the parabolic wave equation or the ray tracing model. And the ray tracing models is just like a set of two ODEs in which you have the first order derivatives only. And do you have any connection between the fractional order derivative and the first order ray tracing models in these sound applications?
No, I don't really, because the this is about attenuation, and first of all, attenuation in water is much smaller than in a sediment, and we have fairly good models for attenuation in salt water, for instance, where there are relaxation processes due to boric acid and what is the other one? Magnesium sulfate, I think, are the two main ones, plus viscosity. And so there are only three relaxation processes, which usually needs to be taken into account when you're dealing with underwater acoustics, say from 1 kilohertz to a megahertz or so. And so, and fractional derivative models or power law, general power law models are in a way equivalent to a very large number of relaxation processes, much larger than 3. So it's better to model attenuation in the water by itself by just taking those 3 processes into account and model them directly. So it's not fractional. It's second order with frequency in an approximation, but not fractional, in my experience.
Okay, thank you, sir.
Any other questions? Please feel free to ask. How about the turbulence and fractional calculus? Turbulence is a very hot, open problem still. What do you think, Professor?
What was the concept?
Turbulence and fraction.
Yeah, I had turbulence there because it's a very complex field, but the turbulence here is actually modeled by this drag coefficient here in the circular pore, and that is a turbulence model. This factor is 1 in the laminar case, and then it becomes larger than 1 and increasing with frequency in the turbulence case. So of course there are papers about how to derive these Bessel functions from turbulence, and that's a big area by itself. I'm just taking the models as they are, but these models go all the way back to Biot's paper from 1956, which is the sort of fundamental poroelastic modeling paper, and it's been so here there is turbulence, yes, and half-order models.
Any other questions? Professor Hussein, how are you? Any question? Professor Jordan?
No. I'm very satisfied with the presentation here. I also work on 1/2 and saw that there are many applications in diffusion, heat transfer. Actually, I started for all of my book. So thank you very much, Professor Holm.
Yeah, I'm interested in hearing about other half-order physical models. I actually have a chapter in my book about the prevalence of half-order models, and I was sharing a bit from that. So, and I think there are more models than I've been able to find. So that's an interesting collection to make, I think.
All exists also in surface diffusion of polymers here. I did development of one very old equation of tordite since 65 in different way, how for exists, even though it was derived originally from very, very different point of view.
Mm-hmm.
It works.
No, that's interesting. If you would be kind enough to send me, if you have a paper about this, I'd be very interested. I'd appreciate that.
What I would like to ask, what is your recommendation to construct fractional models for a given process, complex process? What are the main steps? People are asking about it.
Yeah,
usually they replace.
You know, I've sort of you know, I have a postcard with a quote from Picasso. I'm not sure if it's true, but I like it. It's je ne cherche pas, je trouve. I don't search, I find. So, and that's what I've been sharing here. I just found stuff which turned out to be fractional models without me sort of modeling it. So, and I think there are more applications like this, and I'm certainly looking for more such existing models which actually are fractional. And I think it's easier to get acceptance for fractional models in physics if we can find more of these already existing models. So, je ne cherche pas, je trouve.
Yes,
For
yes.
those who understand French.
You don't research, you find.
Yeah.
Yes, yes, that's true. That's true. Young people are, you know, a little bit confused about this. That's why they are always ask what is the meaning, physical meaning, economical, biological for a given model. Why we don't need only non-integer or higher order integer models. Nonlinear dynamics is full of such type of model. Why fractional model? So this is for the moment a hot topic.
Yeah.
And you saw today some of the successful models, and you'll see in the future some other successful fractional models. There are many, and we hope that there will be at least in more than 100 fields where the fractional calculus was applied successfully, because mathematically it's okay. If it is with existence unique stability, it is okay. But the problem is in the meaning. It's a big problem, so not all fractional models are validated. It is clear. So you have, for the ones who are working in mathematical modeling or fractional mathematical modeling, they have to get used to this. There are comments why, give the justification. This justification is not enough, should be more stronger. But you see, for particular alpha, if you dig into the problem, like Professor Holm did, like you see also for Jordan tomorrow, they will find for specific alpha. But for any alpha, then it's a matter of thinking, not a matter of searching, and like give the interpretation of alpha for in general. It's an open problem. For many years, we discussed these things in many conferences with physicists, with biologists. Look at the COVID, so many models. Where we are going, what is the best? Is it fractional, not fractional? Not fractional. Is there any other question? Carla, do you have a question or other colleagues?
No, I'm fine. Thank you. Thank you.
You
Congrats
also
to
were
Professor
talking.
Holm.
Other colleagues. Daria, do you have a question for Professor Holm?
Not now, Professor, because
Good.
it's clear talk.
Okay. If there is no other question, we thank to Professor Holm. Also, I like to thank to Professor Tenero Machado. Your very nice top-level talks, which cover many things in fractional and non-fractional and beyond, and many open problems were revealed. We hope that young people got some new ideas. There are many new ideas explained by two top-level researchers. So I wish you to have a pleasant conference. And nowadays, now I will give the microphone to Professor Nejati. Thank you, Professor Holm, once more.